able to solve that thing over there? So I'm going to give the first step, which if you miss it, that's the end of you. So the first step is that we apply the Morgan. You apply the Morgan there, the Morgan's law, and what you get now is that that thing up there is equal to x prime multiplied by y prime times x plus y. Okay. So I just put the multiplication symbol here just to emphasize. So maybe I should take it off because it will get you confused with the notation. So this is what you get. This, and this. Are we there? All right. Sorry? Please, I cannot get you. Whoever is talking, if you're not talking, please mute your mic. Quebo, are you the one talking? Quebo, are you the one talking? The sound is poor, I can't get you. All right, so that's the first step. That's the Morgan's law. So can we continue from there? Let's see what you get. All right, so this right here, just apply the Morgan's here. You get that is equal to x prime. This becomes multiplication. It's easy to miss it out. It's easy to miss it. It becomes multiplication. That's why I'll not put a sign there where you want. Yes, any worries? Any concern? All right, so solve there. Let's see the final answer you get. So if you do that, from here, that y prime as answer. From this y prime. Professional sectors is fine. People will draw, even draw if they got on the screen. It's fine. Even there on the board, they still print it on their book. Sorry about that. Using equality sign, if it's equal to, say the statement above is equal to this is equal to this. Don't just write like literature.
X, y prime is equal to x.
X,
Y prime. X prime.
Yes, I'm solving and so it's, of course. So you now have x prime, x plus y. Use the double negation rule here. Double negation. And now you use distributive law here now. Distribute it x, y prime, x plus x, y prime, y. Okay? X times x. Y prime times y. Which is that one? Y prime times y is 0. Because if y is true, this one is false. If this one is false, this is true. And if this one is true, this is false. If you multiply two opposite things, they always give you 0. For example, and. Multiplication is and. So this has to be true and this has to be true. For it to have true here. So this will always give you 0. I'm just putting a dot there for multiplication. X times 0 is what? God. Anything plus 0 is what? Plus and all. Is that thing. Alright, so here we'll apply the double negation. So x prime prime becomes x multiplied by y. And then we can now apply the bracket x plus y. X plus y. And the law we have used here is a double negation. And the next step, you could now have the distributive law. So you have xy times x plus xy. There's supposed to be a prime somewhere. I missed it. So y prime. I missed a prime here, right? And then xy prime times y. And which law have I used here? The distributive axiom, or the distributive law. Is that okay up to that point?
Yes, sir.
All right. So it's worth noting that the multiplication operator, I'm just ignoring it because x times y, we just always represent it as xy. There's no point putting the x there. All right, so from here, which law are we going to apply to the first term? The first term here, you see that you can use the commutative law to rearrange so that you have x times y prime. So you use commutative law, you have x times y prime, and x times x is x. And here you have x multiplied by y times y prime is 0. Which leaves us with x times y prime plus x times 0 gives us 0. And anything plus 0 gives us that thing, which is the answer. So that's what we'll get. All right. Is that okay? Anybody who's not clear with this exercise? You're not clear? Okay, so what's your challenge? When to apply? Don't know when. I've not get the first part. When to apply a law. When to apply a law. Okay. So which law do you know when to apply? You apply a law based on what you have on the ground now. So, but if you can look at this thing and apply another law, there's no problem. Man. If you could look, some other person might look at it as this x multiplied by x prime plus y prime or prime plus y multiplied by x prime plus y or prime. That's incorrect. I've not violated any law, I've just used the distributive law. I've distributed this with this and this with this. But you cannot take only this one and distribute when there is this prime here. So you need to see that this prime applying on all of these things is a challenging thing for you. If you don't see that as a challenging thing, then there's a problem. It means that you have not understood the laws of logic. So, but if I look at it and see this negation, it looks to me like P or pure or not P or pure negation. That's the equivalent in propositional logic. This and this is the same. Okay? And you see that this negation can be applied inside here to have not the sign changes. So the only way to know is to study. Do more exercises and you look at more examples, you might start understanding how to apply the laws. So you felt ready to read the laws and know the laws are. Look at what is possible. Because if you don't know what is possible, you don't know how to apply. So that's why I said for us to move to the next section, you need to promise me that those two things that I am after those two things. So promise. So when I come to my next hour, I'll give a quiz. Just on those two things. Quiz. But if you don't know those, that's the foundation of logic. If you don't know those two things, this one will become a bit difficult. Because what we are doing now is that we are applying all the laws in predicate, in propositional logic, in addition to these new laws in Boolean algebra. So we did not mention the Morgan's law here, but you are just seeing that the Morgan law also applies in this case. I don't know how else I can teach it. I don't know how else to explain when to apply a law. It's a very difficult question. When somebody steals, what do? You go to the pinnacle and look. When you see what they do, you get the right hand side. So you look for where you see the left hand side, and then from the left hand side now you can say it's equivalent to this. Or if if you see something already on the right hand side, you look for the right hand side and then you check what the person did. You go to prison, this one says the sentence 12 years and hand level. You go to the code. What happens why would somebody be sentenced 12 years hand level? You look at the other side. You kill somebody. You see, so either you replace you kill somebody or you give that sentence. It's just the same thing. So the laws of logic. If you go somewhere and you found something that was very simplified like this, there are times when you want to take this one and put it in this form instead. When you have something like this, you instead reverse it to be this form. There are times when you see this one, you want it to be this form. There are times when you see this one, you want it to be this form. So you should be able to see the law in both directions. You should be able to move from here to here or to take from here back to A. Okay, let's proceed. Hoping that there are no issues. All right. So the reason why we have been doing all of these things is because we want to get into digital circuits. Because you see that the whole concept of designing digital circuits is based on Boolean algebra. Okay? And we know that in a circuit, you can only have two things happening in a circuit. Either there's going to be current flowing through a particular part of the circuit or no current will be flowing through that part of the circuit. So that's why Boolean algebra addresses the design of circuits. Because when a current flows in a circuit, then that part of the circuit will have a 1. And when there's no current, you have a 0. So here is a truth table for Boolean algebra, which is something that is implied. And see here now that the table is kind of reversed. When we were doing propositional logic, we started with true, 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 false, false, true, false, false, which is actually 4 or 3 down to 0. So we had 3, 2, 1, and 0, which we converted to those true and falses. Now we have actually reversed the order. We start from 0 down to 3. You know that 0 is 0, 0, 1 is 0, 1, 2 is 1, 0, and 3 is 1, 1. That's in Boolean, in binary equivalent, in base 2. And if you look at the truth table, you see that for the addition sign, which is the OR, it's only false when both x and y are 0. It's only 0 when both x and y are 0. And for the AND, it's only true when both x and y, or it's only 1 when both x and y are 1. And that can easily be seen from the circuit that we showed above, where in one case the switches were connected in parallel for the OR, and in the other case the switches were connected in series for the AND. And there you have the complement, where the complement of 0 is 1 and the complement of 1 is 0. A digital circuit, or what is called a logic gate circuit. You hear a lot on logic gates, logic gate, logic gates. So a digital circuit or a logic gate circuit is an electronic device for performing digital computation. So you use a logic circuit to perform digital computation. You might want to produce a calculator where you are able to add two numbers. You can actually combine some logical circuits such that when you put the two numbers here, it adds the numbers and gives you the output. Yeah. So if you want to do an adder where if you put 3 plus 5 inside, the output will be 8 in binary. You can do that with logic. You figure out a way to combine the bits to give you the output. So that's one main reason why digital circuits are important, because they can permit us to do digital computation. So a good example there is a processor of your computer, which is doing all kinds of computation. So when something enters here, it's able to carry out and or not, all those operators, all those operations happens within the processor, which will permit you now to have some output. Please, just 1 minute. Where are you? Oh, okay. Alright, some interruption. Okay, so where are we? Digital circuit, logic gates. Okay. So we say digital circuit is an electronic device for performing digital computation. I was just trying to say that the processors of your computer actually is like digital circuit, and it has all of these gates integrated within it, so it permits you to carry out all kinds of computation. It has a number of inputs, so any digital circuit will have some form of inputs, each of which is an electrical circuit that can take one of two states, either a 0 or a 1. So this, you see that these 0 or 1s will actually represent some low or high voltages in the system. Either the system is conducting or it's not conducting. So generally a 0 will not be a 0 voltage, it will be a very small voltage, because in every digital circuit some current or voltage must be found in every component. If not, the component is not working. So you might liken maybe a 12 volts to a 1 and a 0.5 volts to a 0 in the circuit. For any given combination of inputs, the device computes one or more outputs, each of which is either 0 or 1. Okay, that's true. All right, so you find out that a digital circuit is made up of something called logic gates. So logic gates will form the building block of any digital circuit. Logic gates. So logic gates are the smallest components of a digital circuit. Now, if you look at the diagram there, you find out that a logic gate basically has some inputs and then gives out some output. Or a digital circuit more generally would accept some inputs and have some output. What you find out there in the middle, which is not represented, is a digital circuit, which may contain one or more logic gates, which may have one or more building blocks for digital circuit. Now we are going to look at some basic components that would make up a digital circuit, and these are called gates or logic gates. The first type of gate that we can use is the OR gate. The first type there is the OR gate, and it's represented with that shape there, the OR gate. So see that the OR gate takes X and Y as input and gives you X plus Y as output. Gives you X plus Y as output. Now for the AND gate, it takes X, Y as input and gives you XY as output. So it's an AND. So we saw the truth table for an AND. The output is 1 only when both X and Y are 1. And for the OR gate, the output is 1 when either X or Y is 1 or both X and Y are 1. So it still gives you a 1 as the output since it's an OR. The next symbol there is for the NOT gate, or what is called the inverter. The NOT gate or the inverter. Now please, these symbols are just representation. It means that if you're going to the market to buy a NOT gate or an inverter, don't expect to see it having that shape. It's just a representation of the gate. So if you went to the market to buy an AND gate, don't think that you find something that looks like this and then that's the AND gate. No, this is not how you find in the market. They're just symbols to say, if you want to represent an AND gate, this is how you draw it. And if you want to represent, it's just like a representation. All right. So those are the symbols. So if you look at the first example now there, to draw a circuit for the Boolean expression x prime plus y. So imagine that you have a circuit which has the expression x prime plus y, which means it is something equals to x prime plus y, right? Maybe the output is equals to x prime plus xy prime plus y. So we're actually saying that one is circuit where the output will be x, y prime plus, I don't know that what is there. So it means something will enter like this, some magic will happen here. We wonder the output should be this. So we have something simple like this. At the end of the day, you want to have one output. And the output, the input should be what? y prime is not an input because y prime is coming from y. It's the same variable. Y prime and y is coming from the same variable. X and x prime is coming from the same variable. So if we were to achieve this, then you see you have what we have there. If I were to try to explain, you have the two inputs, x and y. The first thing you see is that the y is what? You negate the y now, you invert the y, which means you introduce an inverter here or a NOT gate that position. The next thing I see is that I need to get this, I need to do the AND of x and y prime. So it means that here I have now y prime behind this place. Y enters, now I have y prime. I need to look at the AND. And if I were to do the AND, I'm going to use the AND gate. Okay? That's the AND gate. Okay, so that's the AND gate, which means at this point, what I have now is x y prime. I'll apply the AND gate on it. Okay? And now I need to take this and OR it with y. So I need y. So if I need y, I cannot take y from here because it's y prime. I'll come and get y from here. And what do I need to do with y? Sorry, you don't see what I'm doing, but you can actually see the output from on the screen in that example. Maybe if you have difficulties understanding that diagram, we'll look at it. Let me just explain it briefly. Okay, so this is what you have, and now you need to take this, which is y here, and do what? OR it, so you apply now the OR. Is there anybody who has not seen the difference between the OR and the AND gate? You cannot see the difference. Maybe you need glasses or you don't see the difference between the diagrams. So this is the output. That's the output. Have I made a mistake? No, I'm not. That's the output, which is x prime plus y. So it means if I were to produce a system where it will take x and y and manipulate it in this form to give some output, then I need to go to the market, buy a NOT, an inverter, buy an AND gate, buy an OR gate, and then I come and connect it. Okay? And which means anytime x will have a particular value, the current flowing through x, then I'll know the output. Anytime the current is flowing through y, I'll know the output. Anytime the current is flowing through x and y, it's going to give me particular output. Okay? So we have 1 and 0. Yes, are we having any difficulties understanding this diagram in example 1? So you see that the inverter is used here to change y to y prime. And so after the inverter there, this line here will have y prime. Now y prime will now add with x using the AND gate to produce xy prime. And you need to now OR x, y prime, and y. So that's why y is now tapped from before the inverter into one of the arms of the OR logic gate. And then this now gives us the output x, y prime plus y. Is that clear? Is it clear?
Yes, sir.
All right, fine. Yes, okay, that's the second example. So we're trying to draw for x prime plus y all primed and multiplied by x plus y. So try to follow that on your screen to be sure that it is correct. Try to follow up that to see if it's correct. Is that okay? Is example 2 okay? Are we able to reproduce that same diagram? X prime plus y. So you add those two things, and then you negate everything. And then you now AND that with x or y. It's correct now? Nubia, is it correct? Is there anybody who cannot distinguish from an OR gate from an AND gate? The symbols. The symbols are distinct, right? Yeah, they're distinct. So one has the OR is curved. The left side is curved for the OR. All right. Okay, so that's what we'll get. If you look at it again, you see that it's okay. So how many components have we used in that circuit? How many logic gates have we used? Yes? Example 2, how many logic gates have we used?
5.
Somebody else says 3. Daniel, how many logic gates have we used?
5.
5. Okay, any other answer?
Yes, sir. 5, sir.
Okay, 5. All right. So do we see that there are 5 components? Yeah, but what's the bed? So if you okay, so if you went to the market you want to construct that gate, you are going to, how are you going to use the components? Imagine you are building a component that needs 4 1.5 volts battery. Are you going to buy one and use it as 4? So you need to actually buy the physical things. So you need to buy 5 components. Okay, so that's a bit it's a bit costly for us to buy 5 components. Now I want you to realize that, or to notice that the example that I asked you to simplify was actually for that circuit. The exercise I gave you some moments back to simplify a Boolean expression. Okay, and the output was, can somebody remember the output? So the answer was x, y prime. Can we see there? Yes, so when we simplify that Boolean expression, the answer was x, y prime. Which means what? Which means that all of that circuit there is equivalent to x, y prime. So can we now draw the new circuit, x, y prime, which is equivalent to that complicated thing that you have there? So try to draw the circuit. So if I want to draw the circuit, I could use software to draw circuits. I could draw it's x, y prime. So it's an OR. Was that an OR? X? No, it's an AND. So x and y prime draw lines. Okay,
So what are we supposed to do next?
I was saying that the circuit, I was saying that the circuit that you saw earlier, which had 5 components, okay, had actually given you that Boolean expression to simplify. And when we simplify, this is what we had. xy prime. Can you remember? So that circuit that you find there with 5 components can actually be simplified to get x and y prime. So what I want you to do is to draw the Boolean, the circuit, the digital circuit for x, y prime. Okay?
That's a mute my mic.
Sorry? Are you there? So that's what we are trying to draw. So if you draw, you have something like what I have. Just that mine is, maybe you have to rotate what I have. Just have to rotate what I have. Can I group this? Let me see if I can rotate easily. Need to look for the rotation tool. To group it, connectivity, invert. So I should be able to rotate this stuff. I don't know exactly how to rotate it. Let's see. Export. But it doesn't really matter. The orientation is not very important. But that's what I have. So you should be able to get something like that as well. Let me just see what these students here have. Let's see what you have. I think most of you have the answer. So, please know the difference between and or. This one is straight here. This one is curved there. This one is slope. This one has the slope is more gentle than the other one. And also, all right. So I have my own diagram there, but it's kind of inverted or upside down or whatever, but it doesn't really matter. Are we good in Douala?
Yes, sir.
All right. So is that the same output that you have?
Yes, sir.
All right, good. I just want to learn how to invert this thing. Just do some trial and errors. Flip vertical.
So I know how to flip it.
Flip horizontal, okay. Why is it not flipping? There's supposed to be a handle. Yeah, how do I do it? There's supposed to be a handle somewhere.
Just watch my screen.
Okay, so I unshare mine. Are you using DR?
Yes, sir.
All right. Okay. Yeah, I can see your screen. Just go ahead.
I've seen the one that I can use with
Horizontal.
Wait, no.
Is to do.
There's another one.
No, you're not in the right. That's not the. You're not in the right mode. Just go to your tool, the widget that you're using. You should be under logic.